Okay, today it's quite raining. I mean, it's raining today. It's raining heavily since last night here in Skudai. I'm not sure about where you are. It's very dark right now. Anyway, I hope everybody is safe. Nobody is involved with any flooding. Another one more thing I need to remind you guys. We're going to if for example during the final you are affected by the flooding, you can request for a special test. You don't need to sit on that same day as everybody else. You have the right to request for a special test for your final. And another one more thing, if you are having internet problem during any test or any final, you have to submit a request from UTM to use to have your test or your final somewhere close to any university which is nearby to your place. You can request that. But the deadline is quite soon, if I'm not mistaken. It's I'm not sure what day is it today. Today is the 10th. I think today is the deadline for you to submit your request. Okay. Having said that, I hope everybody is having the internet at home. No problem with the internet, and that everybody goes well during the test. The third test is coming soon on the 20th. Today is already the 10th, so another 10 more days. And also your final will be somewhere in February. I got the date here. I forgot what date it was. The date they have already scheduled the final for every subject. So I'll let you guys know soon. Okay, so let's start. I'm not going to display this barcode anymore. I will do that later on towards the end of the lecture. As usual, we'll be looking or we'll be continuing with our lecture based on what we have done. Okay, I'm not sure when we did this, but previously we have done this. We have done this example, and when we did it, we just calculate the heat of the reaction. We were not looking at how to calculate the energy balance, even though I did mention towards the I think I did mention how to calculate the temperature outlet. That was the unknown. I did mention how to solve it, but I did not go through it in detail. So we did calculate the heat of the reaction for this example. In this example, you have ethanol. You have ethanol over here. It is dehydrogenated. That means it produces hydrogen and acetaldehyde. That is example 953. Today, we're going to use the same example, the same equation, the same reaction, but we'll be looking at example 954. So take note of the heat of the reaction, which is 69.11. We're going to use that value. We're not going to do the calculation all over again, but the example is slightly different. We'll be looking at example 954. So let's go to 954. Okay, here you go. Okay, this is the same example. So I'm going to write down the value of the heat of the reaction for this example. 69.11 kilojoules per mole. It is an endothermic reaction. That means in order for the reaction to proceed, you need to supply it with 69.11 kilojoules per mole of heat. Okay, so now let's read through the statement of this example. You're going to form you're going to form acetaldehyde from ethanol. At the same time, you're going to produce hydrogen. Your feed is at 300. The diagram is already here. So let's look at the block diagram or the flow chart. Your feed contains 90% ethanol and 10% of acetaldehyde. The acetaldehyde, even though it is being produced, it is also inside your feed. Okay, the amount or the flow rate of your feed is 150. I think the author made a mistake here. There's a typo error. It should be per second, because if you take note of the flow rate on the product on the outlet. In the outlet, the flow rate in the outlet is per mole per second. So obviously the feed should be also in mole per second. So now the questions, the statement says that the temperature, in order to prevent the temperature from dropping too much and thereby decreasing the reaction rate to an unacceptable low level, the heat need to be supplied to it. The amount of heat supply is going to be 2,444 kilowatts. And this will result in the outlet temperature of 253 degrees C. The question asks for the fractional conversion. It didn't ask for the rate of heat input or the rate of heat output. The heat is already mentioned in the question. The amount of heat that is supplied is already given. The value is 2,444 kilowatts. The outlet product N1 is not given. Previously, when we did a few examples, the amount of the flow rate or the product, the flow rate of the product is given. So right now, for this case, you need to do your meter balance to calculate N1, N2, and N3. So as always, the first step would be to assign a basis, since the flow rate of the feed is given, so you're going to use that as your basis. The basis is going to be 150 mole per second of feed. This is the only feed that is coming in, so you say of the feed, there's no other feed. Fine. If you have more than one feed, then you need to specify that 150 mole per second is actually for what? Is it for ethanol? Is it for acetylene? Is it for hydrogen? You need to specify because there's more than one feed. For this case, it's just one feed, so it's sufficient to say it's 150 mole per second of your feed. Okay, that's done. So now we're going to do our material balance. I'm going to do it slightly different. I'm going to do it both ways. Your textbook uses the atomic balance. I'm going to use the extent of reaction balance. The extent of reaction that we have done. We have been using all this while. So I'm going to draw my table. I'm going to construct my table. I will have my first row that will be for the component. My second row will be for the input. The third row will be for the reaction. And the last row will be for the output. Let's put this is input or the amount coming in, which is mole per second. Your plus minus means plus if it is being produced, minus if the compound is being consumed. So your coefficient and the extent of reaction, since we're going to use the extent of reaction method, mole per second. Okay, I'm going to undo that. I'm going to undo that because I'm going to put bracket over. Okay. Next, output. That's going to be mole per second. And we're going to have our first component that will be ethanol or C2H5OH. That's your first component. It's not a straight line. I'm going to have acetaldehyde as my second component. And my last component is going to be hydrogen. That's my last component. I'm going to tidy up a bit. Let's see. Okay, I'm going to tidy up so that I have some space over here. I might be able to use that space. Okay, done. Okay, so what do we have coming in? Input 150 times by 0.9. If you multiply for your ethanol, the total flow rate is 150. You multiply with 0.9, that is the mole fraction, you end up with 135. You do the same thing for your acetaldehyde. So 150 minus 135, which is the 10% left, that will give you 15 mole per second. There is no hydrogen in your feed. Okay, so if you look at the reaction, the formula, please check the formula. Is it balanced? Sometimes the reaction, the equation given is not balanced. You have to check whether it is balanced. In this case, I know it is balanced because this is from the textbook. But if you have a test, if you have a final, check whether your equation is balanced. For over here, you have 2 carbon, and that's 1 plus 2. That's 2 carbon. Your hydrogen is 5 over here, so that's 3, and that's 1, that's 4. And oops, did I get it right? Oh yes, there's 6 hydrogen over here, so it should be 6 on the left, on the right hand side too. 3 plus 1, 4, 4 plus 2, that's 6. So everything is balanced. Your oxygen is going to be 1 on the left hand side. There's 1 oxygen on the left hand side. There's 1 oxygen on the right hand side. So it is balanced. We don't have to worry about that because this is from the textbook. It is balanced. But if you have your test, if you have your final, even though the reaction is given, please check whether it is balanced. It might not be balanced. There might be typo error. There might be it might be purposely done to make it unbalanced so that you balance it. You know, because you just need to check it. So now your coefficient in front of ethanol is 1. The coefficient in front of acetaldehyde is 1. The coefficient in front of hydrogen is 1. So every component has a coefficient of 1. So we don't have to worry about that. So since ethanol, if it's based on this reaction, ethanol is going to be consumed. So that's going to be minus 1. Your acetaldehyde is the one that is going to be produced, plus 1. Anything that is produced will be plus. So the bracket will contain your extent of reaction because it is based on this formula. Okay? So your extent of reaction will be in the bracket, but we're going to leave it blank because we're going to solve for the extent of reaction by looking at the table. And now what do we have? We have N1 as the outlet of your ethanol. N2 is the outlet of your acetaldehyde based on the block diagram. And N3 is the outlet of your hydrogen gas. And all of these compound or gases are coming out at 253 degrees C. Your input is supplied at 300 degrees C. So the temperature is there. So every time you need to do energy balance, you need to have the temperature. Without the temperature, there's no way you can calculate the enthalpies. Okay. So there's no way you're going to be able to solve this because you don't know what is your extent of reaction. I'm going to put it here because there's no way I'm going to be able to solve for the output. I can only write down the output 153 minus. Okay, that's the equation for N1. For N2, 15 minus the extent of reaction. For N3, that's the extent of reaction. How I get it? I'm just go through this whole, through the column. There's no input for hydrogen. You have one extent of reaction, so you plus it out. You end up with the extent of reaction for N3. You do the same thing for acetaldehyde. You have 15 here. You plus the extent of reaction, so you end up with. Sorry, I forgot. I made a mistake there. Should be plus, because there's a plus sign there. So 15 plus the extent of reaction. So do the same thing for ethanol, 135, minus, why is it a minus? Because it is being consumed. So I'm going to raise this, that is the same level, 135 minus the extent of reaction. So that's your material balance. Unfortunately, you can't solve it. So what is required in this example? You need to find the fractional conversion of ethanol. So I'm going to write that formula first. Since I have this space over here, the number of ethanol in minus the number of ethanol out divided by the number of ethanol in. So that's the equation for fractional conversion. And I do happen to have the amount of ethanol coming in, but I don't have the amount of ethanol coming out because the value of extent of reaction is unknown. So I need to solve for the extent of reaction. And I don't have any other information except that I have to solve for the energy balance since the amount of heat given is provided. The amount of heat supply to the reactor is provided. So I should be able to solve for the energy balance. So write down the equation, the H, the extent of enthalpy, the change of, not the extent, the change of enthalpies, the change of kinetic energy, you should always write this equation in full, even though you know that you will end up with Q equals to delta H. The heat supply is equal to the change in enthalpy. Even though you know that, but you need to write this equation in full, because you need to drop off certain terms, and you need to give your reason for dropping it off. And so kinetic energy will be dropped off, change of kinetic energy, change of potential energy, the shaft work will be cancelled off. Give the reason. Why is there there's no change in kinetic energy? Because there's no change in velocity, or there's no acceleration. Why is there no change in potential energy? Because there is no change in height or elevation. Why is there no shaft work? Because there are no moving parts. Okay, so state it down, because that's very important. You will lose mark there if you do not write it. So this is going to be your, I'm going to write it over here because I do happen to have the value of my heat supply, which is 2,440 kilowatts. And that, if you look at the change in enthalpy, since we have a reaction, if we are using the extent of heat of reaction, that will be your extent of reaction, your heat of reaction, plus outlet, your product of the molar flow rate with the corresponding enthalpies, minus the inlet, the product of your molar flow rate with its corresponding enthalpies. So that is the equation that we have used before. If you are using the extent of reaction method, or if you are using the heat of reaction method. So just now we did get the heat of reaction. This value we got from the previous example, 453. So we have that value. I'm going to write it down. It's equals to the extent of reaction is the unknown. 69.11 is my heat of reaction. Okay? But I don't have this part of the equation yet. So I need to construct myself my table as always. Okay, so in order to do this, because I'm using the heat, what method I'm going to use? I'm going to use heat of reaction. So I'm going to first I need to construct my table. Then we decide what reference state we're going to use. Alright, so I need, how many rows do I need? I have 3 components. So 1, that's not straight, that's terrible. 1, let's get that straight. 2, 3. I have my ethanol. C2 H5O4. That's my ethanol. Gas. Write it down as gas. My acetaldehyde CH3CHO. That's in the form of a gas. And lastly, I have my hydrogen. Yes, I need to know the phase because my heat transfer coefficient, my heat capacity dependent on the phase, whether it's liquid, whether it's solid, or whether it is gas. So next, I need to have my inlet and in. The unit is mole per second. That's 1. Next, my enthalpy in, that's kilojoules per mole. Yeah, I'm not getting a straight line there. I wanted it to look straight. Try to get it straight. Okay, and out. That will be mole per second. Enthalpy out, kilojoules per mole. I'm not going to draw a straight line there. It's done. Okay, the amount in, we already know the amount in from our material balance, 135 for ethanol, 15 for acetaldehyde. There is no hydrogen coming in. The amount out, we do have this equation, 135 minus the extent of reaction, and out for acetaldehyde is 15 plus the extent of reaction, and for your hydrogen, that's N3 is equal to the extent of reaction. So we need to calculate the enthalpies. Let's say this is enthalpy 1. I need to put it to the side. so that if once I have the value, maybe I can write it down here. H1, H2, I have H3, H4, H5. Right. Reference state. Remember to state down your reference state. You are going to use the heat of reaction method. So your reference state, you can use the compound that is in the reaction and any inerts that is present. So you have your ethanol, gas, you have your acetaldehyde, gas, and lastly you have your hydrogen gas, and at a temperature of 25 degrees C, because your heat of reaction, your standard heat of reaction is at 25 degrees C, and the pressure is also at 1 atm. So you're going to use that as your reference state. Alright, so now we need to look up the value of the polynomial equation in appendix B1. Oh no, B2. Sorry, I'm going to find it. I'm going to just write it down. I'm not going to speak through it because I'm going to try to save some time over here. I'm going to do this same example twice. I'm going to write it down. Okay. Unfortunately, for acetaldehyde, the value is not given in the appendix. Okay, I'm going to write down the CP for acetaldehyde. Actually, it's already in appendix. In example 593. This is the CP for acetaldehyde. Yeah, that's the CP for acetaldehyde. It's already there. Okay, so I'm going to write it down in our example 954. So I have three components here, so I'm going to write all three of the components. The value of the polynomial value for the equation. Okay. Trying to get a straight line, not getting a good straight line. I have my ethanol here. I have my acetaldehyde and my hydrogen. So you should be able to get the values from your appendix. So let's write down the ethanol. I'm just listing it down because it's easier when you have it. You can see it is visible, so that is easier. Or else we'll be going back and forth looking at our appendix. Okay, that's A, B, C, D. Okay, let's erase this extra space. Maybe we will use it later on, just in order to look better. Okay, now for ethanol, if you look it up in your appendix, this is going to be 61.34 times 10 power or minus 3. Okay, the B, value of B is 15.72. You can check it out. You can check your appendix whether I got it right. If I might make a mistake, please do check it out. Minus 8. And for the D is 19.83 times 10 to power of minus 12. So that's your D. For acetaldehyde, it's already given in the previous example. I'm just going to write that down. 13.26 times 10 power of minus 5 minus 8.05 times 10 to power of minus 8. I'm trying to make sure that everything is correct. For hydrogen, you can get it from the appendix at B2. This is from appendix B2. The only information that we don't have is for acetaldehyde. So that is given in the previous example, example 952. So you should be able to use that same value because it's the same reaction. Anyway, even though it's different reaction, but you're just looking for the polynomial value, the polynomial values for your polymer equation. So it doesn't matter what equation it is, but it's as long as it is acetaldehyde. These are the A, B's, C, D's values for your three components. So if we're going to get for H1, so it's for ethanol. So we're going to H1. the integration of ethanol 61.34. I'm trying to squeeze everything in one line, so I hope I can do it. T minus 8.749. That's the reason why I display the coefficient. But you see it and you just it's easier this way. I forgot my T square. I need to erase that. I need to erase it because it's crowded. That's T square plus 19.83 times 10 power minus 12 plus T to the power of 3 dt. So this is your polynomial equation. Your reference state, you mentioned that every component is going to be at 25 degrees C. So you start with 25 degrees C. And now for our H1 enthalpy 1, that is for the inlet. And let's go back to our block diagram. The inlet, they are all at 300 degrees C. The temperature for the inlet is 300 degrees C. So your value over here will be 300 degrees C. So somebody please do the calculation. When I did my calculation, I got 23.147 kilojoules per mole. Somebody double check that. I'm just going to proceed to continue, but you guys please double check that calculation. For H2 enthalpy 2 is for acetaldehyde. Yeah, for acetaldehyde, same temperature in the inlet, so that's coming in, the inlet temperature is 300, so that will be 300. Your reference state is 25, so that's the lower limit. So for acetaldehyde, I'm going to just jot down the polynomial values. You guys please check my calculation for H1, whether is it the same as mine. I did it earlier, last night actually, because I wanted to save. Oh dear, I forgot to write the temperature. Okay, temperature. Minus T to the power of 2 plus 2.38 times 10 power minus 11 T to the power of 3 with respect to temperature. That is another equation that you need to solve for. When I did it last night, I got 19.132 kilojoules per mole. Somebody please check. What's the value of H1? Did anybody manage to get H1? Enthalpy 1? Anybody? Anybody going to respond to me? Am I speaking alone? Let me see, how many participants do I have? I have 26 of you guys. Somebody please respond.
Doctor, I got the same.
Same. Yeah. Okay, thank you, Faisal. Muhammad Faisal. And how about H2? Anybody? Have anybody calculated that? Anybody get a result, value for H2? Still in the process of calculating? Okay, let me proceed to my H3. Yeah, H3 is for ethanol, but it's for the outlet. You do have the outlet temperature, which is 253 degrees C. So I'm going to use that temperature in my integration, 253. So I'm going to do the same calculation, except that the temperature is different, and it is for ethanol. 253 degrees C is the outlet temperature. The reference state is 25. So I'll be looking at ethanol, 61. Again, I'll be repeating the same equation for ethanol. In the meantime, please calculate for me the values for H2. And if you already managed to get H2, proceed to get H3. Now this is minus 5 T. Do not forget the temperature. And it's 8 T squared plus 19.83 times 10 to the power minus 12 T to the power of 3 dt. Okay, done. For that, you should be able to get a value. Okay, for H3. We do the same thing for H4. I will ask you guys for the value later on for the values. So we just continue with our equation. Again, the same temperature, outlet temperature. Now we'll be looking at acetaldehyde. H4 is for acetaldehyde. I have acetaldehyde here for H2, so I don't need to look at the table. I will just look at the equation for H2. That is for acetaldehyde. Here, 2.38 times 10 power minus 11 T to the power 3 close the bracket with respect to temperature. So that is for acetaldehyde. And lastly, I will have the enthalpy 5 for hydrogen. Again, you start from your reference state and you end up with the desired temperature, the temperature of interest, which is your outlet temperature. Okay, I'll be looking at H5 is for hydrogen, so I'll be looking at the coefficient of hydrogen. Unfortunately, I cannot fit everything in one screen unless I zoom out. Okay. Okay, should be able to get it. That's 28.84 times 10 power minus 3 plus 0.00765 times 10 power of minus. No, there's no. Should there be a minus 0.0 times 10 minus 5? I forgot here, guys. Yeah, times 10 minus 5 plus T, there's a T there. 0.3288 times 10 power minus 8 T square plus, oh dear, I don't think I can fit everything in. Times 10 minus 12 T to the power 3 with respect to temperature. Right, close the bracket. Right, so let's check whether our value for hydrogen is correct. Go back to appendix P2. This is P1. Okay, I'm going to zoom in. This is P1. You need to go to P2 just to double check whether I got my value, the A, B, and C and D for hydrogen is correct. Let's go through this. There's hydrogen. It's going to be hydrogen gas. That's hydrogen gas. The equation is in the form of 1. Your temperature in the temperature degree C, that's 28.84. Double check it. Then 0.00765. That's 0.3288. And lastly, minus 0.8698. And they are all multiplied times 10 minus 3, minus 5, minus 8, minus 12. Okay, we got that correct. So let's go back to our example. So now please get the values. Somebody give me the value for enthalpy 3. Anybody? Nobody? Not sure? What I got, when I did it, I got 18.516. You need to know how to calculate your enthalpy. You do not use your calculator. It's very straightforward. You do not have to, 253 minus 25, then 253 square minus 25 square. That's the long step. You just plug in the values using your calculator. The calculator automatically calculates the integration for you. So you need to know how to do that, because I came across in test 2, there are students that doesn't know how to integrate directly using the calculator. So anybody, did you get the same answer as me for H3? Anybody, did you get a different value? Because I really need to get I need to verify whether mine is correct. Somebody, please respond. Nobody going to respond? Gosh, you guys. You're really in a very bad... Okay, I'm just going to write them down. If it's wrong, then we will get the wrong answer. When I did last night, I did not arrive to the correct answer for the fractional conversion. So now you have to verify whether I got it right. Okay. So all the enthalpies are calculated. So I'm going to put down the values in our table. I'm going to just write down the values. H1 23.1447. Did nobody want to respond?
Same answer.
Guys, Same answer for every enthalpies?
Yes.
Thank you, Nabila. Thank you very much. Appreciate it. The rest of you guys, are you still sleepy? It's raining the whole night here in JPE. The weather is just nice for sleeping. Okay, so everything is there. So now, all we have to do is plot these values inside this equation. Okay, so I'm going to do that. I'm going to erase this. I'm going to use that equation to get our unknown, which is the extent of reaction. Okay. I'm going to put the outlet. I'll be looking at the outlet for ethanol. 135 minus the extent of reaction times by its enthalpy, which is 18.516. This is going to be a very long equation. Plus for acetaldehyde, 15 plus the extent of reaction multiply with the corresponding enthalpy. Yeah. And plus for hydrogen, the extent of reaction and its enthalpy 6.595. So that is for your outlet minus for your inlet. For your inlet, 135 is for ethanol and its enthalpy 23.147 plus for acetaldehyde 15 is enthalpy 19.132. Close the bracket. So that whole thing is going to be 2,440. The only unknown in this equation is your extent of reaction. Solve for the extent of reaction. I don't have the value, guys. You have to do the calculation for me. It's going to take some time, but eventually you will get the answer. I'm not sure whether I have expanded the equation or not. Let me see whether I have expanded. Let me see whether we can simplify it. There's not enough space for me to simplify. There's not enough space for me to simplify. Okay, let me try to simplify it. Okay, 69 point. Bring out the extent of reaction. 69.11. Okay, that's the first value there. The other value will be that minus for the extent of reaction. Yeah, that's the second value. Next, if we look at the equation, the other value will be 15. That's a plus 15.375. Where is the 375? Yeah. Next, any extent of reaction anymore? We have this one plus 6.595. Okay, now let's check whether there are any more extent of reaction values. No, that's it. We have 1, 2, 3, 4. That's it. So close the bracket. That is your extent of reaction. And now you need to multiply that value and this value. You need to multiply. Or you need to get both of it. So that's plus. Both of them are plus. So plus 135 multiply with 18.516 plus the other value, which is 15 times by 15,375. Yeah, that's plus. Now the second part of the equation, which is the outlet. This is the second part of the equation, which is the outlet. Yeah, so we're going to repeat that. minus 135 with its corresponding enthalpy minus 15 with its corresponding enthalpy. That is equals to, if we go back to the equation, 2440. That's minus, so it should be minus there, okay? 2440. So let's do the calculation then. Whether we're going to come out with the same answer as the textbook. 69.11 minus 18.516 plus 15.375 plus 6.595. Okay guys, if I got a wrong value, please correct me. Plus do not just follow, do not just get the value from me without double checking it. The values are quite big. If I do any, if I have miscalculated, please please inform me. Because we want to get the same answer as the textbook. Hopefully, we can do that. Let's do the calculation for the right hand side. 2440 minus 2499.66 minus 230.625 plus 3124.845 plus 286.98. So the value I got is 3121.54. Therefore, my extent of reaction, if I divide that by 72.564, 43.0177. Anybody get a different value? Or 18, round it off, then let it be 43.018. That will be in mole per second. Write down the unit. Okay, now, since you already managed to get that, now we'll be going back to our material balance, putting that value for your extent of reaction, which is 43.018. Somebody please double check my calculation, whether it's right. If it's wrong, please let me know. So now I'm going to proceed with the value of extent of reaction being 43.018. I'm going to put that inside my bracket here. Okay, so we'll be able to calculate our output, 43.018. 43.018. I'm squeezing everything in. Okay, so this will be 43.018. That will be 15 plus 43.18. 15 plus 43.018 will give you a value of 58.018. Yes. And for your ethanol, 135 minus 43.018, the answer is 91.982. Okay, done. You have your output now. So you continue to calculate your fractional of conversion. 135 minus your output for ethanol, 91.982 divided by 135. So what answer will we get for our fractional conversion for ethanol? Ethanol is the only the statement of the example state that you need to find the fractional conversion of ethanol. Even though you have acetaldehyde in the feed, it is not required because acetaldehyde is not the one that is actually your main input. your main feed. Your main feed is ethanol. So 135 minus 91.982 divided by 135. That gives you a value of 0.31. Round it off, actually it's 87. So we're going to round it off to 0.319. So what answer is given in your textbook? Let me have a look. Where is it? Let's see. Anybody? Do you have the textbook with you? What is the answer for the fractional conversion? I need to look it up. Okay, let's see. The answer from the textbook is 0.319. Wow, we got it. The same as the textbook. We got the same value for the fractional conversion of ethanol, which is 0.319. The textbook did it using the method of heat of formation. The material balance was done using the atomic balance. We did it differently. We did the material balance using the extent of reaction, and our energy balance, we did it using the heat of reaction method. So you can compare both methods. Any questions? Any questions? This example is considered quite a good example because it involves both the material and energy balance that need to be solved simultaneously in order to get the desired unknown. Right? So it looks kind of threatening, but it's just a bit long. You just need to be patient with calculating the enthalpies, especially the enthalpies, because that's where most students get stuck. Right? Once you have done that, all you have to do next is just to solve for your extent of reaction and put it inside your material balance. You'll be able to solve for the output. Any questions? Any questions? Anybody? Everybody? Everybody's clear on this? Wow. I hope everybody is fine with this. Everybody is clear on this, because you'll be asked maybe something like this in your test or maybe in your final. Things like this. This is one reaction. So you can use the heat of reaction method. There's only one reaction. If you have two reactions, then most probably, it's very likely for you to use the heat of formation method if you have two reactions. But if you have only one reaction, it's easier to use the heat of reaction method. Now, let's look at it from the solution given in the textbook. We're going to use the heat of formation method. When you do the heat of formation method, the energy balance. Okay, before that, use the atomic balance first. I'm going to erase that. The atomic balance using for the material balance. Hold on. I'm going to undo this. I'm going to start all over again using a different page so that it be easier for us to have a clean sheet. So we have a clean sheet to work on. Right, so I'm going to copy. I'm going to go back. I'm going to create a new note. Okay. Why am I not be able to? Why I'm not able to do that? Hold on. It's now 9.4. I did copy it. Okay, that is erased. This is the example. Copy. I'm going to go to my notes. New notes. There's my new notes. Paste. Now, that's the same example. We're going to solve it using the heat of formation method and also using the atomic balance. Yeah, so let's look at the energy material balance first. Basis is the same as what we have done, 150 moles per second of your feed. Okay, now we're going to do your atomic balance. We're going to have a balance on carbon. Only carbon. So for ethanol, how many carbon do we have? 1 carbon for ethanol. Okay, so I'm going to erase this so that you will not, I can't erase it because I copied it from previous example, so I can't erase it. So now, your ethanol, you have, initially you have 150, the amount of ethanol coming in, mole per second of ethanol. Yeah. And 1 mole of ethanol will have 2 carbon. There's 2 carbon. 2 mole of carbon. But there's 2 there. Okay, there's 2 there. So that's your carbon. There's 2 carbon. So plus the other compound coming in is acetaldehyde. So 150 times by small fraction of mole of per second of acetaldehyde. Acetaldehyde, I'm going to not have enough space here, so I'm going to just give it a short form of AC. Okay, acetaldehyde. Because I don't have enough space, I need to squeeze everything in. So that's acetaldehyde. And the number of carbon in acetaldehyde, there's only one carbon there, there's another carbon there, there's 2 carbon. Okay, so there's 2 carbon, 2 mole of carbon in acetaldehyde. That's your input. Now looking at your output, because when you do your material balance, it's always input equals to output, because you're using this for, this is just atomic balance. So input equals to output. There's no consumption, there's no generation, it's just output and input. So next we look at the ethanol. In the output, you have 2 carbon there. So you have 2 carbon, so going to do the same thing. That's N1 mole per second in your output of ethanol. I'm trying to write everything, squeeze everything in. So 1 mole of ethanol, you have 2 mole of carbon. Plus your acetaldehyde is N2 mole acetaldehyde. I'm going to give it a short form, acetaldehyde per second. And 1 mole of acetaldehyde will have, let's look at our acetaldehyde. We have 1 carbon here and another carbon there. So that's 2 mole of carbon. Yeah. So when you rewrite everything, we cancel off the units. Then you end up with just carbon. Because this is your material balance on carbon. So you will end up with 135 when you multiply 0.9 times by 150 times by 2 plus 15 equals to 2N1 plus 2N2. So that's one equation, but unfortunately you have 2 unknowns. You can simplify this further. Can you? Can you simplify this further? Let me see whether I made a mistake.
Acetaldehyde, one carbon only.
Acetaldehyde, 1 carbon only?
CH. Okay, sorry.
You got 2. Okay. Let me see. Why is it that I'm getting something quite different? Okay, no, this is correct. 135 times by 2 plus 15, what is the answer? Is it 300? I got 300. 300 equals to 2N1 plus 2N3. Okay, so if you let me erase this, I'm going to write it in a simpler form. You will end up with N1 plus, no, N3, this is N2. Okay, N2 plus 250. That's your first equation.
Doctor, it's 285. Yeah, 285, not 300.
285?
No, my calculator says 285.
Time by 2. Sorry.
Yeah, I did it. 135 times 2 plus 15.
You see? 135 times by 2 plus 30. 300.
Ah, yes, because the times 2 of 15, is it?
Yeah, I forgot 15 just now. I forgot this. I forgot to multiply by 2 here.
Okay.
I need to multiply by 2. Sorry. Yeah, so it should be 300. So that's the first equation. 2 unknown cannot solve. So now you do your balance on, for example, what balance do you want? You can do on hydrogen, because if you do on oxygen, if you do your balance on oxygen, you end up with the same equation. Okay, so now balance on hydrogen. For hydrogen coming in, let me use a different color here so that we can see what I'm doing. I have 5 hydrogen there. I have another hydrogen there. So that's 6 hydrogen for my ethanol. So balance 135. I'm not going to do the cancelling of the unit because we know what to do with the unit now. We have 5 hydrogen plus 1 hydrogen, that's 6. So that's times by 6. Yeah. The next for acetaldehyde. For acetaldehyde, I have 3 hydrogen here. I have another hydrogen there, so I have 4 hydrogen. So that's 15 times by 4 is equals to, for the outlet, again, I have my hydrogen in my ethanol, that's 5, plus 1, that's 6. So and 6 and 1 plus for acetaldehyde, I do happen to have, as I mentioned just now, I have 3 here, I have 1 there, so I have 4 hydrogen. So 4 and 2. And I have also hydrogen in hydrogen gas. So that is going to be 2. Okay, so and 2 and 3. Okay, so when you do the calculation, after you have done it, you get what is that? 135 times by 6 plus 15 times by 4, you get 870 equals to 6 and 1 plus 4 and 2 plus 2 and 3. You simplify it, you will get, when you divide by 2, that is 435 equals to 3 and 1 plus 2 and 2 plus 1 and 3. That's your second equation. You have 3 unknowns now. You have 2 equations. Is it possible to solve it? Can't solve it because you have 3 unknowns but 2 equations. So what you have to do is you have to do your energy balance. Okay, so from equation 1, maybe you can get N1 is equal to 150 minus N2. And when you substitute it inside the second equation, let's try to do that. 435 equals to 350 minus N2 plus 2 and 2 plus N3. You will get, let me do the calculation, 150 times by 3, 435 equals to 450 minus 3 and 2 plus 2 and 2, and you have another unknown and 3. So now we have 2 unknowns. So let's bring everything over to the other side. So it's 3 and 2 minus 2 and 2 minus N3 is equal to 450 minus 435. That's equals to 15. You end up with 1 and 2 minus N3 is equals to 15. That's your equation. After you have substitute N1 equals to 150 minus N2, still you got 2 unknowns. You have 1 equation left. So you cannot solve it. So you need to do your energy balance. Now let's do our energy balance using the heat of formation method. I'm trying to get a straight line there. Oh, it's not getting a straight line. Well, let's see. We have our ethanol. We have our acetaldehyde. What's the formula? CH3CHO. And your hydrogen. gas. Yeah, all gases. And in mole per second, do the same thing. That's what we have done before. I said that now we'll be looking at it using the heat of formation method. Oh, it's not straight. Yeah, and out. Oh dear, somebody. I got the wrong unit here. That should be kilojoules per mole. Yeah, so this is going to be mole per second. And out. Fish out. Kilojoules per mole. Okay. Now, the amount in this now is the same thing as what we have done before. So nothing new here. H1, H2, we have the amount out. We don't know what's the amount out. We have N1, if I'm not mistaken. That's N2. That's N3. So that's H3, H4, H5. Alright. So we're going to use the heat of formation method. So our reference state is going to be the elements that existed in its natural state. So we have carbon as a solid, we have oxygen gas, and we have hydrogen gas. And the temperature must always be at 25 degrees C and 1 atm. Yeah. So what we're going to do, we're going to start with the elements, we're going to form the compound. After we have formed the compound, then we need to heat it up or we need to cool it down, depending on what's the temperature. So now let's look at our inlet. Our inlet is at 300 degrees C. So we'll be heating it up from 25 degrees C to 300. So the general equation in order to get your H is to get it in to get the heat of formation from appendix B1, and then you integrate from 25 degrees C to your desired temperature using the Cp of your compound. Right? So let's just show one example. I will show starting from C and oxygen gas and hydrogen gas at 25 degrees C, 1 atm, you're going to form ethanol C2H5OH at 25 degrees C, 1 atm. Well, that will be your heat of formation. That's where the first part of the equation is. Next, you're going to heat it up from 25 degrees C to your, to your desired temperature. Then that will be Cp, depending on whether it's gas or whether it's liquid, from appendix B2. So that's actually how this equation comes about. So that is based on these steps. And so now let's look at for H1. For H1 is the inlet. So your heat of formation of ethanol. So if you look it up, I already got that value over here. I think I need to, instead of proceed with the calculation, I'm going to write down all the heat of formations for our three components. In fact, only two. I don't need the last component. I have ethanol. I have my CH3 acetaldehyde. And for hydrogen. Anybody have the value for hydrogen? Give me a value for hydrogen gas. The heat of formation of hydrogen gas. Anybody? What is the heat of formation of hydrogen gas?
0.
Nobody? 0. Yes, it's definitely 0 because hydrogen existed already in its elemental form, in its natural form. So they don't need to form it anymore. It's already 0. It is 0. It's already in its original state, in its elemental state. So let me see, where did I have that value? I should have got it done. I should have listed it down. I'm trying to find it. For those of you guys who have your appendix, please look it up. You should be able to find it. Not sure where I put that value. It's somewhere here. Okay, found it. Heat of formation of ethanol is minus 235.31 kilojoules per mole, whereas that of acetaldehyde minus 166.2 kilojoules per mole. Okay. So now, if we want to get H1, is equals to that of ethanol. at the inlet temperature, which is 300. So we're going to get the heat of formation of ethanol minus 235.31 plus your integration from 25 degrees C, because that is your reference state. And we're going to go to the desired temperature, which is the inlet temperature. So before this, we already have that polynomial values, which I written before from in the previous calculation. So I'm going to use that same value. I need to squeeze everything in one line. And lastly, your D value. ET. Yeah, done it. So now, do your calculation. We got this value earlier, didn't we? We have done this calculation earlier. Let me show you what we have done for the what did we get for this calculation. We did it when we were doing the same example, but we used a different method, which is the heat of reaction. Okay, now, isn't this the same one? Isn't that the same value, the same equation from 25 to 300 for H1? H1 happened to be for ethanol. Isn't that the same value? So that is 23.147. I'm going to go back to our to this example. So that's going to be plus 23.147. So what's the answer? Once you have done that, you should get the same as your textbook. Now let me see, what did the textbook get? Here the answer is minus 212. I got 160 kilojoules per mole. That is H1, minus 212.163. So put that value here. So that's your first enthalpy. You do the same thing for the others. This is H2. H2 is for acetaldehyde. The heat of formation of acetaldehyde is 166 minus 2. That's what we got from appendix B1. So plus the integration from 25 to 300 degrees C for acetaldehyde. So we have done this actually. So I'm going to go back to that previous example. For acetaldehyde, this is the value that we have got for its polynomial equation. And going from 25 to 300 degrees C, so the answer is 19.132. So I'm going to go back. 19.132. So I'm just going to write the CP here. I'm not going to write the whole thing. Okay. Is equals to minus 1662 plus 19.132, which we got earlier from doing your calculation at the beginning of the lecture, 147.47. Right? We do the same thing for H3. H3 is for ethanol. Going out, your outlet temperature is 253. So you'll be going from, the integration will be from 25 to, so this is your, from 25 to 253. So this is your heat of formation for ethanol. That's your heat of formation for ethanol. Okay? Plus your integration from 25 degrees C to 253 degrees C. I better write down, this is the CP of acetaldehyde. Yes? This is the CP of ethanol gas. Yes, ET. So when you do the calculation, we have done it. So I'm not going to repeat again. Plus, I'm going to go back to the previous calculation. For ethanol, going from 25 to 253, that's the polynomial equation. We get a value of 18.513. Let's see, that's H3. Yep, 18.513. So we're going to use that value. That's going to be 18.516. 16 or 513? Let's see, which is 516, okay. Now, so coming back, that will give you a value of minus 216.794 kilojoules per mole. Don't forget the unit, kilojoules per mole. So next, for H4, your heat of formation. For H4, you are actually looking at acetaldehyde. So as the heat of formation of acetaldehyde is minus 166.2. Now you do the integration from 25 degrees C, 253 degrees C for acetaldehyde. Acetaldehyde, which is in the form of a gas, with respect to temperature. So if you get the answer from our previous calculation, let's get it from our previous calculation. This is the value that we have, the polynomial equation. So we got 15.375. Let's go back to our example. That will be 15.3. Oh, sorry, I forgot again. 15.375. You end up with an answer of minus 150.825. I don't have space to write the unit there. The joule per mole. Lastly, H5. Do I have H5? Yes, I do have H5. That's for hydrogen. The hydrogen heat of formation for hydrogen is 0. You integrate from 25 degrees C to 253 degrees C. Your CP for hydrogen gas, you can get it from your appendix with respect to time. We have done this, so we're going to look at the calculation, the answer from our previous calculation. So this is the calculation that we have done. We got 6.595. We're going to put that value 6.595 kilojoules per mole. So all this information is there. So now all we have to do is substitute it inside our energy balance. 6.595 and this value 150.825. For our H3, we got minus 216.8. We got H2, we got minus 147.07. Done. The only unknown now is your N1, N2, N3. You don't have that value. So using your equation for your energy balance, your equation for energy